Okay, welcome everyone to this continuation of what is algebraic geometry. We are closing in towards the end of what I usually would call classical algebraic geometry. Just one topic essentially is missing, this would be smooth varieties. And then whatever I would call modern algebraic geometry will be next. Of course, there will be a huge over intersections between those, so it's a bit vague what is modern, what is classical, but anyway. So all I wanted to say is that I would like to wrap up now the kind of the classical story, and we definitely want to do smooth varieties because in the end, it's kind of the easiest type of varieties you can imagine. So projective and smooth is usually a very good, very hard criterion to make everything very nice. And yeah, so in order to introduce smooths, we first talk about tangent cones. Actually, there will be two videos about them because they're kind of a little bit, they're important. That's just what it is. And it's all of this comes under the umbrella of a blow up because kind of my idea, certainly not my idea, but my favorite way to sell a blow up is that it kind of make things smooth in a certain way, even if you have singularities around. My favorite example, you'll see that one again anyway, is something like this, where you clearly have some, well, clearly an outstanding point here. We'll see in a. Right now, I haven't actually defined what a singular point is, but this will be a singular point. Okay, so we want to do smooth varieties. So what makes smooth varieties very nice? Well, you can draw a tangent. So whenever you, well, one of the first things you learn in calculus is that if you have a reasonable curve, say it's smooth, then you can kind of find a tangent along a point. This was not so bad, maybe. And this is like the linear, the kind of the best linear approximation. The linear approximation, not the best linear approximation. The linear approximation of whatever type of curve around that point. And you can do the same for essentially anything, as long as it's smooth. Yeah. So if you have a sphere, here's my little sphere. And there's a point on the sphere, as you can see, and there's a tangent plane in this case. So usually you should have in mind that the dimension of the tangent is the dimension of the space you would like to approximate. So the sphere is two-dimensional, and the plane here, or with the tangent plane t, is also two-dimensional. And this is really like the lowest order approximation, where lowest is really degree 1, so linear. Yeah? And clearly tangents are literally everywhere. It's kind of, as I said, it's one of the first things you learn in linear algebra, not in linear algebra, in calculus. Linear algebra is all about tangents, by the way, linear algebra. So we would like to ask the question, what are actually tangent spaces in geometry? Which has a very clear answer, but in geometry we're hitting, at least for the smooth guys, but in geometry we're always hitting those examples here, a lot of them actually. So we would like to know what is a tangent for something when you have a singular point. It shouldn't be very surprising that around a non-singular point, this was really bad, a tangent will be what you think it is. But for such a point here, it's not so clear what a tangent should be, right? So what is a tangent and not singular point? And essentially it works as follows. So here's my favorite example. So here's the equation for that example. And if you think about it, what the tangent should be, well, if you move in from, let's say, the top, and here's a tangent, and then you go a little bit closer, and you go a little bit closer. So let's say you have a little point here that slides down towards the interesting point, and you have a sequence of little tangents following that point, then eventually these little tangents will convert to this type of tangent, right? So if you ignore the other branch that goes up in this case, this is a tangent at that point. But exactly the problem we have is that you can move in from the bottom as well, kind of doing the opposite, and whatever, when you do that continuously, this is the tangent you get, right? So if you move it from the top, you get the tangent that looks like this, and if you move in from the bottom, you get the tangent that goes in the other way. And yeah, this is a bit of a tricky thing. So there's not a well-defined tangent at that space, and yeah, indeed the partial derivatives vanish, which is kind of a bad thing that happens here. numerically. Fine. The only thing I would like to point out for now is, well, maybe we want to make this more rigorous, like moving in from two to... So you kind of take the tangent, all possible tangents together at this point. And maybe the cross itself, the crossing, the green one here, is then the correct notion of a tangent. The one catch we observe here is that it's not a linear space anymore, it's a crossing, right? But it's somehow the best approximation at that point that it looks like a tangent. I just point out that the equation for the crossing is something like a squared minus b squared equals 0. Okay, wonderful. Yeah, that's what it is. Maybe we would try to make that more precise, right? So you kind of, for most points, you have a well-defined tangent, and maybe if you have some crazy point, it should be something like the limit of moving in, or something like that. Okay, so here comes something funny, and this comes, we'll see that later, and I will make that very precise, from this idea of a blow-up. Fine. So let's say we do a change of variables. Yeah? So let's say you put in again a time component. So y is a times time, x is b times time. You just put that in and you get this new equation here. Yeah. So a squared minus b squared, which is almost what we wanted. A squared minus b squared equals 0. And then there's a b squared and x. I just leave it as it is. But at our singularity happens at x equals 0, so we actually get this a squared minus b squared equals 0. And why does it work? So what is actually going on here? It's kind of interesting. So I substitute a time component. Hopefully that makes sense. The whole idea of this blow up is somehow going to time. And I will pull up this little picture that you get. Really, this is just substitution, right? From here to here, this is just substitution. You just do a change of variables. Let me show you how the surface actually looks like. So if you plot the surface, so here's our original picture. Let's zoom in a little bit. Zooming in is always good. So here's our original picture, and the cross is what we call the tangent. And now we pull the cross into space, and this is the equation. Here's the equation. Just I've written it down in different variables, but it's the same equation. And you can literally see the cross here, right? So it's just pulled out in space, and at, in this case, z equals 0, but in x equals 0 on my slide, you will exactly have the cross. And note here what's happening, let's go back, is essentially there should be an approximation, right? So tangent is the best linear approximation, and this should be an approximation on the curve. And everything is of degree 2, except this degree 3 part. So if you want the best approximation, maybe just throw out the degree 3 part and just keep the degree 2 part. And that's exactly what you do. So just throw out this one, and x equals 0, yeah, well, and you get the expected equation for our little friend, the crossing. And that's no coincidence. Kind of extremely strange, but again, this is not a coincidence. It really comes from the blow-up picture. And I've written it down what it means to be a tangent cone, and we had the notion of a cone before. And yeah, so the one catch we play here, I just put it up, we'll stay there on a second, is that whatever is a tangent now is not a linear space anymore. It's a cone. Yeah. Okay, fine. But it has the correct dimension. That's already good, and it kind of does the right thing in this case. I mean, it's not linear, it's a cone. Fine. But again, there's some price we need to pay because we kind of generalized the notion of a tangent. And this is really how it works. And let me rather, well, just to slide it up, fine. Let me rather zoom in into our example. What we actually did is the following. So here was our example. And here was a blow up of the example. And the green line is exactly the pre-image under the projection. Projection goes like this. Of, well, 0, obviously. And 0 is our singularity. So we want to define a tangent. You define it on a point. A tangent cone, you define it on a point. In this case, 0. And what you do is you take this exceptional set and call the cone over that set the tangent cone. Let's have a look here. So here it really is the point, and the pre-image of the point are those 2 points here, the 1, 1 point and the 1, -1 point in projective notation, because remember, my picture is a little bit bad here, but essentially this should be a projective space. Yeah, the time component is a projective space. Fine. So 1, 1, 1 minus 1 are the two type of, what is it? The two type of preimages here, and the preimage of 0 in k squared, or the preimage of 0 in v. So it's either the green line or those 2 points. Yeah, depending on what type of preimage where you take it. It's either the green line or those 2 points. And a cone is usually a union of lines, and it's really the gray thing down here for k squared, which is the projection of the, well, blue lines up here. So we restrict to the ones that touch those 2 points, and they project down to exactly our cross. And that's the calculation we do, right? So that's a cone. So the cone in the whole picture is like this collection of lines, but that's a cone for k squared, for the affine space. And we look where they touch the preimage of my point, and whatever projects down, that's exactly the corresponding cone in our picture, which is this tangent cone. And this is like the lowest order approximation, which I will spend the whole next video to explain how to actually calculate this. But this is kind of the geometric picture. What's happening? It's kind of very nice in some sense. And again, the one catch that you should keep in mind is that it's not a tangent, it's not a linear space in general, right? The crossing is not a linear space, but it's a cone, a union of linear space. But anyway, that's just a price we have to pay. Anyway, I hope you enjoyed this video, and I also hope to see you next time.